There are many tests used to determine whether a series converges or diverges. The typical goal would be to find series that converge, but there are some series that just don't. The first and simplest of these tests is known as the divergence test. It is based on the idea that if you are adding an infinite number of things, the only possible way for it to converge to a finite sum is if the things we are adding continue to get smaller as we go. That is to say, if the series does not converge to zero, if the sequence does not converge to zero, then the series diverges. In order for a series to have a chance at converging to a finite sum, the terms of the sequence, the terms of the series, have to decrease in size. We saw something like this when we talked about improper integrals in a previous lesson. That in an improper integral, we are finding the area of an unbounded space, and that space, being unbounded, goes on forever. So it's an infinite extension of this region, and yet the area can still be finite based on the idea that if if the region shrinks quickly enough to overcome the infinite addition of area, then it can still converge. And that's the basic idea here. The proof of the divergence test is fairly simple, and it involves something called the contrapositive. The contrapositive of an if-then statement takes the conclusion, the then part of the statement, and words it in the complement. That is to say, we would take the conclusion part of this, that the series diverges, and we would say, if the series does not diverge, which is to say that it converges, then, and here we take the premise and negate that. So it switches the premise and conclusion and negates each of them. So if the conclusion of the original statement was that the series diverges, then the opposite of that, that the series converges, becomes the premise in this statement. And if the premise of the original was that the sequence does not converge to zero, then the conclusion here is that the series does converge to zero. Logically, this should make a bit of sense. If the original concept was that if the terms do not shrink, then you cannot, the sum of the terms cannot be finite. This says it the other way. If the series is finite, if the sum is finite, then the terms have to drop to zero. So we're going to start with the assumption that the series converges. And what this means then is that the limit of the partial sums of the series exists and is equal to a finite value. Now, the following two statements must be true. That the partial sum of the first n terms must be equal to the partial sum of the first n minus 1 term plus the nth term. So to break down all of the sum of all of the terms from 1 to n would be the sum of all the terms from 1 up to n minus 1 plus the nth term. This is a true statement. And furthermore, that the limit as n goes to infinity of s sub n will be the same as the limit as n goes to infinity of s sub n minus 1. Excuse me. They both have the same limit, and the idea is that that last extra term is all that separates them from each other. One of them stops at n minus 1, the other goes on and includes that very next term. And that one single term at the end is not going to affect the convergence of the partial sums. So by removing that last term, the limit as n goes to infinity of s sub n minus 1 does not affect the convergence of the sequence of partial sums. Thus, if L is equal to the limit as n goes to infinity of s sub n, which is therefore equal to the limit as n goes to infinity of s sub n minus 1 plus a sub n, through a property of limits, we then have the limit as n approaches infinity of s sub n minus 1 plus the limit as n goes to infinity of a sub n. But as we already said, the limit as n approaches infinity of s sub n minus 1 is still L. So what we have here is, starting from the beginning, L equals L plus the limit as n goes to infinity of a sub n. And it's not hard to see here that the only way this works is if the limit of as n goes to infinity of a sub n is equal to 0. Thus, the terms of the sequence a sub n, the terms of the series, converge to 0. So under the assumption that the series converges, we have shown that the terms of the series must approach 0. Proving this contrapositive thereby proves the original statement of the divergence test, that if the terms of the series do not approach 0, then the series will diverge. This is perhaps best demonstrated with some examples. We'll take an obvious example first. The series 2 to the n, which by the rules of a geometric series should certainly diverge. The terms of this series would be 2 to the first, plus 2 to the second, plus 2 to the third, plus 2 to the fourth, plus 2 to the fifth, etc. It's not hard to see that as we add these together, each new term is bigger than the term before it. This should pretty obviously be approaching a very, very large number. We can look at the sequence of partial sums to verify that. S sub 1 would simply be 2. S sub 2 would be 2 plus 4 is 6. S sub 3 would be 2 plus 4 plus 8. S sub 4 would be 2 plus 4 plus 8 plus 16. And then plus 32. And so on. We can see that the partial sums are, that each new partial sum is a noticeable increase from the previous one. In fact, each one is more than double the one before it. If the sums keep doubling, or more than doubling actually, then certainly the limit of partial sums will approach infinity. And again, that's not hard to see. Obviously, if we keep adding bigger and bigger and bigger things, we will get an infinite sum. To look at something perhaps a little less obvious, let's consider the sum from 1 to infinity of n factorial over 2n factorial plus 1. Starting with n equals 1, we have in the top 1 factorial. In the bottom, we have 1 factorial multiplied by 2, and then adding 1. So essentially, we take the number that's in the numerator, double it, and add 1. Next, we have 2 factorial, which is 2. And in the denominator, we will double that and add 1. 3 factorial is 6. And in the denominator, we double that and add 1. 4 factorial is 24. And then we double that and add 1, etc. Now, admittedly, these are not the most obvious things to see because they are all different fractions with different denominators. So perhaps it might help to look at the decimal equivalents here. 1/3 is, of course, 0.3 repeating. 2/5, of course, is 0.4. 6 over 13 is 0.461, etc. 24 over 49 is 0.489, etc. It's easier to see from the decimal equivalents that these terms do, in fact, keep getting larger. So, while it might not be as obvious because they are all smaller terms, much like the previous example, each new term that's added is bigger than the previous. And certainly, if I continue to add numbers and the numbers I'm adding are getting bigger, then my sum will keep getting bigger and bigger and bigger and approach infinity. In fact, if we were to continue with this, what we can see is that the denominator is always twice as big as the numerator, but plus 1. Therefore, the terms are actually approaching 1/2. By the divergence test, this series would have to diverge because the terms are not approaching 0. Again, the terms do not approach 0 because they are approaching 1/2. Another example would be the series from 1 to infinity of 1 over n. The terms of this series would be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, etc. Now, in this case, the terms are getting smaller as we go. That is pretty clear to see. The limit as n approaches infinity of 1 over n definitely is 0. Now that does not mean that the series converges, but it does mean it has a chance. And that's why this is called the divergence test, because the divergence test can conclusively prove divergence based on the fact that the terms do not approach zero. That does not mean that just because the terms approach zero, that it must automatically converge. So all this tells us is that the series has the chance at convergence. It does not conclusively tell us that it does converge, and it does not conclusively tell us that it does diverge. It only says that we have a chance at convergence since the terms approach zero. So again, the point of the divergence test is not to establish convergence. It's meant to pick out obviously divergent series. There are further tests that are useful for showing that a series actually does converge.